In this slide, we are going to evaluate the effect of PID action on different types of signal. So we have here step signal, pulse, ramp, and sinusoids. So we can imagine if the error in terms or similar to the given function over here, then we can understand what to expect from the output of the controller. So we are going to consider the first controller, which is the proportional controller. The proportional control, as we understand, the function will be similar to the error signal, as we only multiply some value of gain to the value of error, so it will replicate the error shape similarly. The only difference is the magnitude of proportional signal. So we can see that we have similar function to the different type of signal here. So for the step, we have similar. Same goes to pulse, ramp, and also sinusoids. Next, we look at integral function, where integral function will integrate the error over time, which can be simply said the integral function will accumulate the error over time. So we need to visualize the area under the graph will be accumulated over time. So for the step function, we can see that the accumulation will continue, will be started at the step initialization here. So at step time, the error will start to accumulate and will grow constantly, since our step function is also in a constant error value. So next we look at the pulse. So if we understand the integral function for steps, so the initial part is similar, except that at this time, particular time, when the signal value has dropped to 0, which means that if we do the accumulation calculation, here we don't have any error to be added. So the signal should be constant from this time onwards. Next, we look the integral function due to the ramp input. So if we do the integration of ramp, we can see that we have a time squared function, or we can say it is parabolic function, or through visual inspection, if we accumulate the error under the graph here, so we can see as the time goes, the accumulation or the area under graph is increasing very rapidly. So we can say that the increment of the accumulation has been accelerated, or can be represented some sort like squared function. Next, we look at the sinusoid function. So again, we can evaluate through visual inspection. If we look at the area under graph for sinusoid, the integral function will accumulate this error until this point, and then the next point, the area under graph will be negative. So if we look at the accumulation here, when it reach at this particular time, the errors start to reduce. due to the accumulation of the negative. So plus error minus error, in the end we have zero error. And finally, the derivative function. We know that the derivative function is taking the slope of the error signal. So if we look at the step signal, the slope between this time is 0, and then between this time is also 0. But we have some impulse function over here if we integrate this step, which can be seen by this function. It is not practical to produce impulse function, but it can be represented some of the very close to impulse function. Next, we look at the derivative function due to the pulse signal. So similarly, we will have spike over here, positive, and we will have spike over here, negative. Next, we look at the derivative function due to ramp signal. So it is quite simple here. We can see that at this point, we have 0 slope, and then next we have positive slope, but the slope is constant. So we can represent 0 derivative function, and then we can have some value of slope, which is the constant value of slope. Finally, we look at the sinusoid function, where if we see the derivative function, the first half cycle, the derivative or the slope will be high and then reduce gradually until this point, where at this point the slope value is 0. So if we map down over here, we can see the slope initially very high and then it reduced to 0. And same goes to the other sinusoid function.